good morning or good evening, everyone. Thanks for joining from various time zones. I would like to welcome you all for this, the first of its kind webinar conducted by WTO Solutions. This is Madhu Kesavan. I'm the founder and CEO of WTO Solutions. And we are a technology company and we build web solutions, mobility solutions, enterprise and data analytics solutions. That is our primary core forte. We actually have been conducting regular webinars for internal teams, in the sense within the team, like we conduct various discussions, various presentations to grow our team strength, to build the talent, to let them understand all the engineering concepts. That is what we have been doing so far. At the time, we have been thinking that why not we can take such a webinar, such a presentation to the external team, such as to the prospects, clients, business leaders, decision makers, C-level executives. That is what we have been doing today. This is the first of its kind, as I said, the first webinar that we are going to talk about planogram analysis for the open market, in the sense for the external players. So we have our presenter here, Raman. He is around 15 plus years of experience in data engineering, and he is doing various technology solutions, offering technological architect solutions for data engineering, AI, and ML. He also has an international exposure along with multinational companies working exposures. Before getting into this presentation, I would like to tell a couple of points. One is, if you wish us to reach us, you can reach us at that footnote phone number, which is 512-375-4345, or to our email address, bd@wtssolutions.com. And the second thing is, whenever the presentation is going on, if you would like to ask or raise any questions, you can directly unmute yourself and you can shoot the questions, or else you can also raise your the hand raise symbol at the Zoom meeting, so that we should be able to find out, we should be able to let you ask your questions, so that it will be a complete interactive discussions. Also, we have a chat option here. If you want to ask any questions, you can use the chat options so that you can reach us. You can ask any questions that you have. Over to you, Raman Narayanan. Please go ahead and show us what we have got.
Thanks, Madhu. Hi, everyone. This is Raman. We'll get started. So just a small introduction about what we are going to discuss today. So technology has always helped business in many ways. One is to make it stronger. Another one is to make it faster. Sometimes to grow faster, and sometimes to handle very difficult situations. But today we are going to concentrate on another path where the technology is trying to become more intelligent. So it is trying to become more like a human. And we call that field of research as artificial intelligence in a vast terms. So everybody understands what artificial intelligence is, but at the top level. But when it goes into deeper levels, there are many levels to it. So the first step in artificial intelligence, or the first bigger achievement in artificial intelligence, is the machine learning algorithms. And they concentrated more on the classification problems. And the next step, or the next bigger achievement, were the deep learning algorithms. Today we'll be concentrating more on the applications of the deep learning algorithms, which concentrates more on identification and processing. So some of the applications of the deep learning are it's speech recognition, or it is natural language processing, or computer vision, which is very famous and pretty much used in most of the retail areas these days. So we will concentrate more on the computer vision of it. So to begin with, what computer vision is, it's like making computers see, just like how we see, which means it has to identify everything that it sees, classify, and provide more information about it. So the problem is actually complex, but the good thing is there are many algorithms available out there, and the research has taken to a very good place where we have real life problems that we can solve using the computer vision. Some of the applications of computer vision that we are seeing in our news in everyday life is, in the field of agriculture, it can be used for plant disease detection. And then, of course, self-driving cars are very famous, and it's catching up very good. And then one of the application is to find the parking occupancy, so whether there is a free spot or not. And reading text or barcode. So sometimes reading the text can be very tedious. Handwritten text can be tedious. It's a tough problem. But with the advent of deep learning, we are able to do it in a good way. So moving on to the next step is what computer vision can do for retail. So there are many applications, and we'll be seeing some specific problems that will help for retail. But at the top level, one is empty shelf identification. So this is actually a good problem for most of the retail stores, because um, the moment some spot is actually empty, they want to fill it up immediately for a better business. And the next is brand identification. So with brand identification, it becomes very easy for the businesses to say, like, whether all the brands have been there, or whether they have enough resources to refill and things like that. So those kind of problems are being solved, and the computer vision is used in the retail industry on the top level for these kind of activities. What brings together the computer vision across different domains is the object detection. So how to identify what is there in a picture that is submitted to a particular model, and how to interpret it. That's what brings every application together, and that is the core engine. So once we are able to identify objects in an image, then we are in a position to solve one particular problem for that particular field. So what we will do is we will go through step by step and how it is done and what are the technical details that is needed. We'll take step by step. So on the top level, what happens is um, uh, lots of images are collected, and then we are doing a processing called labeling. So once the images are labeled, then an output is obtained. That particular output contains information about the image and the labels that are actually added for that image. Once this XML or sometimes JSON output is available to us, we can actually start training a model. Once the model is ready, then we can start taking input images, and then we'll be able to give an output which will actually tell what are the objects available in a particular image. And for this to happen, we need to exactly train the labels for what objects we want to find. So let's say you want to identify a particular shape like bottle, then you have to train for that. Let's say you want to identify parachute, then you have to train for them. So you have to collect images for that particular object as much as possible, and then create the model out of it. So this is a high level of how the entire object detection process actually works. We will go in depth into one by one and how each things are happening. So in the process of collecting the images, right, there is one big problem. The thing is, it's very tedious. So we have to collect as many images as possible, and sometimes the problem space is kind of not straightforward. So here, all these things are t-shirt. For the human mind, it's very easy to identify that these are t-shirts, but a complex process runs behind it to identify each one of them as t-shirt as far as the computer is concerned, because there are changes in the design, there are changes in the textures, and there are changes that human mind cannot actually process, but we are able to find it as a t-shirt. So in order to solve these problems, right, we have to collect as many images as possible, so that the computer can have the learning procedure perfectly done, and we have a better output using those images. So what exactly is the problem when we are collecting the images, right? So the same image, you take an image and then you run it through the model. It will be able to identify what exactly the object is there. But on day two, if you upload the same image by taking again, the model might not work. The reasons are many. So one is, we all know that we all can add filters on top of the images, right? So the colors and the lights that we are adding on top of the particular object, and the weather conditions sometimes, all these affect the quality of image, and so it also affects the quality of the identification. So the fundamental problem is, how many images can we collect, and how many situations or circumstances, or what is the list? There's no list for that. So that's where the key problem is, and that's where the solution also gets interesting. That how we are training our models, how well we are creating the input resources. So to solve this problem, right, there are few ways. We'll take a look at it. So one is definitely a manual collection, and then adding a lot of different conditions, which is very very difficult. And I'm talking about 200,000 or 300,000 kind of images for a good prediction. So manual collection is actually not the solution, but there are companies that are doing, big players. They are actually able to collect the images, and then they are able to use those images for training. And there is the next concept, image augmentation. So what it does is, it actually takes one image and then modifies it in a variety of ways, so that one image is actually used as multiple images as far as the training is concerned. When it is fed to the training for creating the model. And there is a third method, and that is a synthetic data generation. So this is more about creating images from scratch, creating 3D models from scratch based on the images that we have. This is pretty much the future. But how much we have progressed in this area? Um, Not much until recently, because I don't know how many of you have heard the recent release from AWS, Ground Truth. So they have actually added the synthetic data generation, and what they claim is absolutely amazing, because they say, like, given any object, you'll be able to create infinite number of images, infinite number of conditions, and everything is auto generated. And they say it's about a click away. I haven't tried it personally, because it's very very recent, probably June last week, I guess. So pretty recent. And probably that's the future. We never know if that's the whether it is going to work or not, whether it is going to hold water in the real world is something that we have to wait and see. Though these things have been tried in the past, and then there are few open source solutions already available. But a giant like AWS, who has millions and millions of photographs to start with, actually has a good edge. So how I see this problem, right? So manual collection is definitely, we cannot discard it, though it is tedious and depends upon the situation. That is of the past. Image augmentation is something that we are doing today, on every day, where we are doing the training. And then synthetic data generation could be the future. So the best would be the manual correction plus image augmentation put together for the training that we are doing. And if synthetic data generation works, definitely we can add it to our architecture in creating better photographs. Slightly getting into more details about image augmentation, like what it is, right? As a picturize it. So this is just a sample, just to give an idea, like what happens when you give an image, and when image augmentation happens, several images of the same image is created. Sometimes bend, sometimes with more light, and then sometimes darker shades and things like that, so that the training can become better. Moving on to the next topic. So here, what you're seeing is actually a tool, the screenshot of a tool, and then where the annotation happens. So annotation is the process of creating an output about which part of the image is actually what. So on the left, you see all the options that I have, where I can actually create upload the images and where I want to do the annotation. And these bounding boxes that you see actually tell what these items are. So on the right where you see, these are the labels that I'm having. So I'm actually marking on the image, and then I'm telling to the tool that what it is. So once this kind of annotation is done for one image, then the output that it generates will be in the form of, I mean, in this particular tool, it is more of an XML format. But there are other tools where you will get in a different format, probably JSON. So for each and every image, you have to do this process. So you can imagine the kind of complexity that it has, right? If there is going to be like 200,000 images, then for the 200,000 images, we have to do it manually. And if there are multiple points, then we have to do it in multiple ways. And if there are, the number of labels sometimes might increase after the model is generated, then which means we have to do that. So again, this area is still, in open research, and the best is to do it manually. But again, research has been going on to make it more automated. But as of now, it's still a manual process. This is just a sample of what we get out of that annotation. So we are actually getting the bounding boxes, the x-min, y-min, x-max and y-max, which says which coordinates are actually this particular label is concerned about. So the tool that is going to take these annotations and the images will start doing the training based on these values. This is just to give an idea of what comes out of it. We are moving on to the next problem space. So now we were discussing about object detection and what is the complexity there, right? Even in object detection, we have come to a point where it is slightly different, slightly complicated than the general object detection. So this is shelf detection. The reason for the complexity is because the type of the object it is. Because if you take a T-shirt, or if you take a football, if you take an apple, then those things are pretty much same across all. But when it comes to shelf, right, there is no standard format. So you go to a retail shop and then you see, a pretty standard 5 to 6 shelves, long running and things like that. That is shelf. Again, you go to a fashion store, a dress store, and then you see the kind of shelves. We can't even sometimes we find it difficult to say that it's a shelf, because the way they have arranged it, it's so catchy, but at the same time it's very tricky for the computer to identify them as shelves. So we'll take a look at some of the simple shells and some of the complicated shells and some of the shells that we see on the day-to-day life. So from the human's perspective, it is a simple problem, but from the computer's perspective, it is a tough problem, and even more tough when it comes to training, because we have to train it in such a way that only the outer region is actually taken into consideration and the inner doesn't. So there are solutions are out there. There are probably couple or three different kinds of solutions out there, and we tried different solutions, and then we came up with this. What you see on the left was our first stage of identifying the shells. It was pretty bad. In fact, everything that was square was actually getting identified as shelf, because that's the kind of data that we were trying to feed. We got everything, every kind of shelf, and then we were trying to train it. And eventually, we have come to this point where we are able to identify shelves in a better way. And the brand that you're seeing here is just for reference. We wanted to do something on the real store, something on the real image instead of creating something. So we have taken Adidas as a reference, just for reference sake. And this custom logic that we actually wrote on top of it is actually getting better, and we are still in the process of making it much better. So this particular shelf that you are seeing, right? So this will work only for this kind of shelf, the custom logic. But this custom logic is pretty good enough, because these kind of shells will be used across the stores and pretty much across the countries also. Sometimes brands like Gap, I've seen across the countries, they use the same kind of structure. When you enter into the store, you feel exactly same. You don't know whether you are in the US Gap or whether you are in India Gap. So these kind of structures, once we create the model and keep it, and pretty much they are going to be used for years. That's what is the idea. That's what is the understanding. So now that we have seen about object detection, the self detection, and the deep learning, everything, now I think it's time that we put everything together in the form of what the solution is all about for retail, and what a planogram is. We'll get there. So initially, what has happened before data analytics, right? All the users' data, all the sales data, the business data, everything was actually collected together, and then a, a, a big data analytics engine was used to make it into an information. And finally, there's a plan of execution that they have. They have something that can make the business grow, and they can make the business earn more money. And that's what the companies that are the sales and the companies, they're actually using. And they communicate, the business communicates with the sales and everything with using the planogram. So what is a planogram, we will see soon. But once we have the planogram, then all the object detection and the deep learning that we discussed so far is the engine that uses the planogram and the real images to give us, to show us whether the what the business has planned is actually going as per the plan. So it actually enforces whatever the data analytics is actually given as a solution for the business to grow. So that's where the deep learning, that's where the object detection comes into play. It works hand in hand with planogram. Now we'll take a look at what a planogram is. So so planogram is actually the end of data analytics, we can say, and deep learning is the beginning of data analytics. So we can imagine it that way. So the end of data analytics is to say that what are the items that are actually going to be sold with other items, and in what order, and how to place them, and when doing it in such a way, how efficient it will be, and how much the sales will be, and how much the business will grow. That's what the data analytics is all about, and that's what the data analytics ends in giving a planogram. But once the planogram comes, right, the problem is actually huge. How to actually know whether the planogram is actually being met by the company, or the shop that is actually arranging the items, right? And then whether they are placing in the right order, whether they are putting every item together, or the number of items that they have to be placed. So all these things are the problems that the computer vision will be able to solve. Once the planogram is available, once we are able to take an actual picture of the store, this particular deep learning algorithms and the custom logic that we are writing on top of it, we will be able to incorporate these two images, find the respective values, and give a good picture to the business saying where we stand. So what are for both for the business and sales, right? There are actually almost same, but some of the things are different for the business. Whereas sales stops at a point, but business actually continues. We'll go by one. So for both business and sales, it's very important that the right items have been placed in the shelf. What I mean by right items is, for example, I'm saying, so let's say Lay's is a brand, but there are multiple flavors of Lay's. So we have to know exactly where which flavor has to be placed. So that's what right item is about. So if, let's say in shelf 2, only one particular flavor has to be placed, then only that particular flavor is the right item there. And then the right order. So what to place, when and where, at what time, right? So how to place it correctly, and then the right amount. So this the right amount can be understood from the fashion industry easily. So let's say if there is going to be like 10 jeans placed in a particular shelf, then there has to be 10 jeans there. So if there is going to be two less, then again we have to identify it as there is an empty space there, then we have to fill that. And then enough buffer. Enough buffer doesn't actually come into the um, computer vision problem, because it is more in the back end. This is to make sure that whenever the computer vision actually tells that the values have to be placed, or there is an empty space where it needs to be filled, then we have to make sure that the sales has to make sure that it can come from the back end. So these are the four problems that a sales will have, but a business will have more pressing problems. So sales leave after they place the items, but for the business they have to make sure that the items are replaced immediately, so at regular intervals. And sometimes the customers actually rearranges this thing, so it is the computer vision algorithm has to make sure that these items are found out, and they have to be raised so that they can be put in the proper location. And then constantly we have to monitor the crowd. There is a possibility that suddenly one offer comes in and then people come out, and then there's going to be a huge business. So that monitoring the crowd is also important for the business to make sure that they keep up on the game. So all these things, the majority of these places, computer vision plays a role. And then the kind of reports that it generates can be used by the business as a feedback to improvise. Now we'll move on to the next thing. We have a small demo where the object detection is done using the planogram, and once we take a look at it, we'll see what kind of architecture we have used on it, and then we can proceed from there. I have to move out of the presentation for a while, so I'm just going back on this. Yeah. Hope you're able to see the app. So this is on the emulator. As I mentioned before, we wanted to simulate a real store scenario, so we used Adidas as a reference. So going into the store, and here this is one of the planogram that you see, where you know where the items has to be arranged in a particular way, as we discussed before. And I'm using the picker, and I'm choosing the particular image. So if you look at it, the planogram and the image actually matches. So you can see where the shoes have to be placed, and then, oops, sorry. So where the logo exists, and then where the jackets exist, and where the t-shirts, and what kind of shirts. So there's a one-to-one mapping between the planogram and the real store. So once it is uploaded, so what happens here is now we are running it in the backend. We are not running it on the mobile as of now. So we have an API where the image was sent, and the API has actually processed the image, and we have got the result with a bounding box about what was detected and at what location. So just to give an idea, there were like 12 objects detected, and out of which 5 are the shirts, and 7 are the shelf items totally. So, and the numbers that you see here are the percentage of confidence with which the detection was made. So this is just one layer or one step where after object detection, we collect the metrics. On top of it, we write the logic based on the business needs so that we create KPIs. Once the KPIs are ready, we will be able to send it to the business, and the business will be able to use those KPIs to improvise the process. And even here, you might see some of the things might not be identified. That is on purpose, because some of the objects we did not train. So that is to give you an idea that each and every object has to be trained, and if something doesn't get trained, we can always train it and add it to the model and make the model better, at the same time make the process better. So I'm going back yeah, to the presentation. Yeah. So here is the architecture that we are moving towards, and some parts of it we have already built, but other parts of it are actually in the process. So either either a video feed or an image or anything that is taken from the mobile camera. So there are two ways of processing it. It's one is the edge processing, where the models are actually running on the mobile itself, where there is no need of any internet. And second is the cloud processing, where this is what we have actually done. So where we send to the cloud and get it processed. This particular cloud processing can be a very simple API call, or can be as complex as a complete queue-based system, where if there's going to be thousands of mobiles sending the images all at the same time, they all get queued and the processing happen, and then every mobile gets the push notification based on the image that they have sent. So all this information can be stored either in the mobile internal database or on the cloud, and there is a complete syncing process between the two. So there is a feedback mechanism built as a part of the app where the user themselves can actually add a value, saying that the way the things are processed is not good. Some of the detections are not good. So there is a way they can actually add, and it gets to the backend, and in the backend it gets processed. And once a particular amount of images that were not processed correctly is reached, then automatically we can actually create a retrain mode. And then once the models are retrained, we can distribute all the models to the mobiles, and we can also have the same model on the cloud. So there's a bigger architecture, but the core of it is mostly relying on the object detection, which we were able to actually showcase. So we are coming to the final part of our presentation. So based on all what we looked at, right? So planogram actually helps the business grow. But how better we do, how well we do, definitely matters. What kind of KPIs we take definitely matters. And then object detection supports planogram complaints. So without object detection, we'll not be able to do the planogram complaints. We'll not be able to push forward or give a better results on that. And the third point is, it's a pretty common. Everybody knows that. Everybody says that. So computers cannot do what humans can because of our intelligence is much better, and we are much wiser. But there's a catch there, when not trained properly. So if the training is good, if the training is much better, then there is a possibility that we can make computers, at least try make computers as good as us. And that brings us to the final point. What computers can do, humans cannot. So just to emphasize on this point, right? I've added an image on the left. So what you see here is a very famous object detection image from TensorFlow. You can check out in the examples. So here you see, I think I wish the image is clear, but what it is identifying person, it is identifying kite. So those are the two different objects that it is identifying. But the beauty is, right, there is a kite here which is not actually visible to your human eye, and there is a person here which is not actually visible to the human eye. But the system is able to identify both the kite and the person with a better percentage of accuracy. So this is what it is. So we are actually proceeding in a good direction, and the kind of research and the knowledge that we have put us in a good pedestal, and the tools that are growing on a day-to-day basis actually helping us. Once we put everything together, right, we can actually make technology think like humans to help businesses grow much better and much safer and much faster. And any questions? Hello?
I think that is a nice example, Raman, regarding that conclusion point, like what computers cannot do and what your humans can do. And that is the first time like I am looking into that image, which is really great identification of how it can be trained. So yeah, that's a good stuff. And if we have any questions from anyone, we can Raman can answer the questions. So do we have any other questions?
Hi, this is Sarath here.
Hi, Sarath.
Yeah, I just gone through your slides and maybe your presentation. It looks cool. My question is all about the cost effective. Since we are dealing with the images, how much space and what is the process which is required for the environment setup?
So, I mean, so it depends upon the magnitude in which you are going to do. So let's say if you're going to be concentrating just on one store, then it's not a big magnitude. So you can start on even a small system, small server on an AWS. But let's say you have thousands of stores, then again we have to look into the magnitude at that time. So if you can give me some idea about what you're looking for or the magnitude of the business, then probably we'll be able to give a good idea about that.
I'm just validating about the technical stuff, how it will be balanced with the huge servers, how it can be load balanced with these processes.
I mean, load balancing should not be a problem because I mean, one of the project that I worked on actually dealt with I mean, more than thousands of devices hitting on the server at the same time and then calling on the models. So definitely means, of course, it's a scalable problem, and we have scaled, and it is definitely scalable, and even the models that we are generating, right? So sometimes, I mean, you are right. The concern is right. Sometimes the models can be bigger. It takes more time to process. In spite of it, yes, we'll be able to handle the load. So I mean, I'm confident it can be done.
Yeah, Raman. There is a question from the chat window from Ishwar, like how we can retrain the algorithms. Can you explain more on how we can retrain that algorithms? Required.
Sure. So yeah, to retrain, right? So what the difference in retraining is adding more images and adding more XML annotated files to it. So again, the training pipeline takes more time. Sometimes it runs from 6 hours to 10 hours. That's true. But once we have these files in place, the retraining happens through the script. The entire thing is intact. Only the files change. So we have to change the files and re-trigger the pipeline for retraining.
Ishwar, does it answer your question?
Yeah, it's fine actually. Yeah, I got the answer. Thank you.
That's good. So the next one is from Rajesh, like for a small scale retail planogram different than warehouse, like if there is any difference between the term planogram analysis for a small scale in the warehouse, and what is the efficiency of the
Yeah,
model that you're
definitely. When it comes to small scale, we will be able to train it better because we will be able to identify the problems easily, and we will have more control. But when it comes to the big chains, the data increases tremendously, and the number of images that is needed is significant. For example, the number of conditions that happens is significant. I can give you a small example. So let's say we have a T-shirt which is hanging in the hanger, right? And that by itself has got like 15 to 20 scenarios. Just by blowing some wind, the way with it changes, right? So the number of images that you want to take is more. So similarly, if there is going to be more items, the combination and the different conditions on top of it, the complexity increases. So the smaller, the easier to control. The bigger, it is definitely going to be more time consuming, more problematic. But again, nothing to worry, because the bigger the problem, again, the solution is also coming very stronger. And the tools that we have today, we are in a much better position to hammer it in a much better way.
That's good. I hope that answers some Rajesh's questions. Anyone else? Any other questions?
Hi, I've also got a question coming basically from a need from big retail players in the market. A lot of them are contracting other companies to basically carry out inventory of their products. And I'm just wondering if this model could also count basically how many items are on a shelf or come up with a prediction. And if so, how accurate would that be?
um, I didn't get the question fully. So is it
Sure,
like
I can help you on that one. So Radu's question is calculate that inventory. Like if there is a shelf, and if you want to figure out like how many, for example, like an lace chips packets over there. What is the inventory available in the shelf? Will the model count the inventory of the shelf?
Exactly. The model will give you. So to be okay, let me put it precisely. The model will give all the metrics which we will be able to use it to count the number of items on the particular shelf. So we'll get all the shelf details, all the items in the shelf detail in their arrangement and everything. But let's say if you want the count, we can take the count. Let's say you want the arrangement, we can take the arrangement. So anything that you want can be calibrated from what we are able to get from the model. That's what is the idea. Does it answer your question?
Yes, thanks a lot.
Yep. And primarily, Radu, one more point to add on that one is obviously like this is an identification of the shelf, but eventually for inventory calculation in the sense like we need to consider like what we have in our like an stock. I mean, like if the items are not placed in that shelf, or even if one item is hidden behind that second item. Let's say that you have around like a 5 lace chips packet hidden behind one behind one. I don't think the model can identify that 5. Is that correct, Raman?
Yeah.
Yeah. So that is an like an potential use case risk here. If you want to identify the inventories, all the products or all the inventories should be visible to the model. If it is hidden behind one existing item, then it is going to be tough for the model to identify.
That makes sense. So
Yes.
it needs to be visible.
Yeah.
Whenever it goes as input in the model. Thanks a lot.
Yep. Thank you.
Yeah. Can I ask a question related to whatever you told right now?
Please, Ishan, go ahead.
Yeah. See, you were telling about if the objects are hidden behind actually. So can I take it for granted that this particular algorithm does not use a three-dimensional space for identification, or it just identifies by the I don't know how to put it across. Like for example, you've got a particular volume at a particular shelf where you can keep if the shelf is full, right? If you are able to find out one object has got so much of volume, right? And if the shelf volume is so such that it can occupy 5 packets of that, right? Is there our algorithm is so this thing that we cannot find out that if it is hidden?
Yeah, this is a very case to case. We have to solve this per case. So let's say if we are going to deal it with food based retail, then we have to solve it differently. If it is going to be dress based, then we have to solve it differently. So this is a very peculiar case, right? Specific case. So we have to handle it specifically. But yes, we can use the three-dimensional case to figure out how many items are there. This is a general way. But when it comes to specific problem, then we have to add our custom logic on top of it to make sure that we are having the right value.
Okay, great. Thank you.
I think Gangadharan has actually raised his hand. Probably is waiting. Gangadharan, do you want to ask anything?
Hi, good evening. No, I just when I entered into that, I said hi to the people.
Oh, okay. Hi. Okay.
I don't have any questions about it. Thank you.
That's fine. Yeah, I just wanted to make sure. Yeah.
Anything like
else?
Another question from business perspective, sir. What I'm asking is how effectively today this particular concept is being used in the business scenarios in an Indian context as well as in a global context. Is it getting picked up very fast, or it is still on a trial basis or something like that?
So in the global context, definitely the US market, it is picking up very fast. So I've seen some of the products, some of the people are actually, very aggressive in getting it happen. And this is the future. I mean, we are at the tipping point. So
Okay.
if you're going to have the same question probably next year, right? This
Yeah.
question might have been outdated. So because the media might have been flooded with the number of product companies that are booming on doing this particular thing. So we are actually on the tipping point because, as I told you, right? So even the AWS release the
Yeah.
last week of June, right?
Yeah.
That is expected to be a game changer. The kind of problem that field had was because people did not have enough images to start with. But now, if they
Okay.
don't depend on any of the retail stores to start building their models, right? That is the
Yeah.
game changer. And once the number of models that's going to come, I'm pretty sure there are going to be, plenty of open source models out there. And I wish this question becomes outdated soon, so that both
Okay.
of us, you and me, will be
Yeah.
enjoying the benefits of the industry.
Great, sir. Great. Thank you very much. And you feel these companies like online retail companies can take a terrific out of advantage out of this, or do you think it becomes a disruption after some time?
No, I mean, as far as computer is concerned, right? So it
Yeah.
doesn't matter whether it's online or whether it's a real store.
Correct.
So it's it's pretty much anything that comes in, and then you give a comparison value. You find the patterns in the underlying thing. If the intelligence can be used in the online market, which already is being used, yes,
Yeah.
it can be used there. So as I told, right, the object detection is the life of the all the applications. So once we have object detection, once we have all the values in place, then writing a layer on top of it to fit our application is actually the simpler problem, which we have
Correct.
already mastered. So what we have
Correct.
not mastered is the object detection, and that's where we are concentrating more. So once we
Okay.
have the data, then everything is a cakewalk after that.
Okay. Okay.
But
Super.
ideally, like that brings up another interesting scenario in the sense, um, online scenarios obviously, like how the market will be or how Planogram will help online.
Yeah.
Instead, if it is online in the sense, it has to be an analytics. Either it could be an Hotjar analytics, or it could be an any other Google analytics, or this 360 analytics. That kind of an analytics will eventually help where the customer moves and what kind of an purchase action that they are doing.
Yeah. Customer
So
journey
I,
inside the store you're
yes,
seeing in the online space.
yes,
Yeah.
that is completely different than this kind of an brick and mortar planogram analysis at the moment.
Yeah.
But might be like as Raman said, like moving further, definitely like the customer journey will merge between online and offline. Let us say like there will be a bridge between online and offline. So like if a customer prefers some specific planogram model in offline, he might be getting that exclusive access or exclusive view in his online portal also.
Correct. Correct. Correct.
So that kind of collaboration might happen in future.
Yeah, because there are buying journeys where the customer might not be very comfortable in buying something in
Ah,
online. For example, you
ah.
don't buy a car today in online, right? So you have a stores and you have a online analytics about car only. But if you really
Mm-hmm.
want to finish your sale, you go to the real physical space and buy it, right?
Yep.
So those kind of things can be linked, I think, if you use the planogram application perfectly, right?
Yep. Yep. Mm-hmm.
Yeah,
Yep. Mm-hmm.
correct.
That's good.
Great, sir. Very interesting, sir. Thank you very much for giving us so much of information. I think we are really setting a journey for a new technology and a new
Okay.
this thing.
That's
Yeah,
great. That's great.
thank you.
I think like
Thanks a lot.
we are on track with regards the time, and
Yeah,
I think like
thank you.
we just have around six minutes to wind up the meeting,
Yeah.
and
Okay.
we will go for yes. Thanks, Raman, for this presentation, and Vikram, would you like to take out the call and give the closure note?
I can
Yes,
put back the.
that was a. Yep, I'm sorry.
You go ahead, Vikram. Sorry. Yeah, go ahead.
Yeah, that was a good session, Raman. Thank you for that. And I would like to thank all the professionals who has joined with us today and make this session more interesting. We have no words to offer gratitude for your valuable presence here. I would like to thank our Honorable CEO, Mr. Madhikesavan, and our data architect, Mr. Raman Narayanan, for spending their valuable time. We will be happy to share the recording session to your email shortly and keep you informed on the upcoming useful webinars. And once again, thank you for joining with us today, and you all have a very wonderful day. Take care and bye-bye.
Thank you so much. Thanks, everyone. Have a great night. Bye.